Hi, ladies and gentlemen. In this video, I would like to iterate what was covered in the course regarding distance and distance protection for high voltage lines. Distance protection is being applied only to utility lines, to transmission lines, and traditionally it will never be applied beyond 50 kV. Since the standard around 50 kV is 63 kV and up, so I would say you will find distance protection only above 63 kV lines. Transmission lines are different than utility distribution lines in the fact that transmission lines in many cases are in parallel, as opposed to distribution that is rarely, just rarely, in parallel. And we would like to protect those lines in two different ways. The main protection, and always the mandatory one for transmission lines, will be differential protection, ANSI number 87, and that will be the most important and the fastest protection we will apply for transmission lines. But now, as a backup, we will apply distance protection as well. The question is, what exactly is distance protection? We have a transmission line here in front of us, and that transmission line is long. It carries a lot of voltage, in most of the cases above 138 kV. So we are talking about 138 kV, 163 kV, 250 kV, and so on. In North America, it's quite common to use 500 kV, but that depends on the length of the line. The longer the line, the more losses we have on the line, and therefore we will upgrade the voltage higher and higher and higher to cover for those losses. A transmission line is not just simple three wires that are going from A to B, but it is a full and a complete electrical system that includes capacitance to ground, capacitance to the poles, inductance for each and every stretch of the line, and simple resistance due to the distance of the transmission line. And that's what we see here. Between A and B, we will have two transformers at least. One at the beginning of the line and one at the end of the line. Many problems will apply, and it's supposed to be taken into account in a transmission line, including the fact that when it starts it might be, for an example, 500 kV, and when you end you will get something like 550 kV. And this is due to the Ferranti effect. During the length of the transmission line, we have for each and every component of the current its natural impedance and another impedance that comes from the mutual effect of the three phase on each other. And we have to keep in mind that we have an impedance that is different than the natural impedance of the line due to that mutual impedance effect. A fault can come on the line anywhere. It might be on the transmission line during its transfer from the power station to the main station, to the substations, and on the feeders after the main station. Basically, during the measurement of values on a transmission line, we are measuring impedance. We have current, we have voltage. Current and voltage means impedance. V over I, impedance. And that's exactly what we have on that stretch of the line. The line starts at A, ends at B. During that stretch, we will have several impedances. One during the generation, one during the stretch of the line, and one due to the load. We will measure and follow this impedance all the time, and due to a fault, the moment we see a drop in the impedance, we will notify that with a CT measuring the current down to the protection relay. The protection relay will evaluate how much is the drop and how fast is the drop. Based on that, it will jump to a conclusion that it is a fault and trip. That trip is our protection on the line. If we will allow the current to run on and on and on during a fault, the line will melt. And that damage will be costly. So in this case, what we have a current of 1000 amp for an example, and 1 kiloamp is running considering the load generation and the length of the line is a good condition, a nominal condition. On nominal conditions, we apply no measures. When we have a fault in that location, for an example, like one of the phases is touching the ground, the pole, or one of the other phases, the current will jump to a value which is much higher than the nominal current. That might be 10,000 amps, 10 kiloamps, as we see in that example. Current can jump 8 times, 10 times, 20 times its nominal current. The relay will see the increase of current, which means a decrease, a fall in the impedance of the line, and jump to a conclusion that it's supposed to trip. The relay is sitting right here. When we say sitting, we mean CTs and VTs. CTs are measuring the current, VT is measuring the voltage on the line. We must have those two measurements in the same time. The relay can look to a certain distance of the line. The distance of the line is being represented by its impedance. So we look into the line and we are reaching up to that point. We can reach, meaning look at how healthy is the line from here to that location, which is below the length, the full length of the line, beyond the full length of the line, or even much farther to cover our line, the next line, and part of the next one. As well, we can cover the area before the relay, which means we are looking in reverse. Reverse looking relays are being applied in most of the cases. Each one of those stretches and reverse is known as the zone of protection. The zone of protection might be looked at as an area we should not go in. If the impedance goes down, 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 and it enters into that circle, that means that we have a fault. The zone of protection not necessarily will be described as a circle. It can be described as a circle, as a lens, as a rectangle of a certain shape, and of course, as we said, backwards. The first zone will go to about 80–90% of the length of the line. The second zone of protection will go to 120% of the line, meaning the full line plus 20%. And the third line will go all the way beyond the first line, second line, and 20% of the third line. When we look in reverse, for zone 4, we are looking at about 25–30% backwards of the line. That's for reach. When it comes to timing, zone 1 has no timing. The moment we see a fault, we trip immediately, no waiting. Zone 2 is a full length of the line, including part of the next line, and traditionally we will apply 0.25 of a second, 250 milliseconds, up to half a second. When it comes to zone 3, we will apply 1 full second. The possible faults are multi-phase faults, or phase A, B, or C touching ground. So there are 4 different possibilities of a fault on a transmission line when it comes to current increase and decrease, fall of the impedance. To help with the speed and decision making of the clearing of a fault by the relays, we will have one relay at the beginning of the line and one relay at the end of the line. They can communicate. Not necessarily, but in most of the cases we will connect them together with a communication line. That communication channel can transmit from relay 2 to relay 1 or from relay 1 to relay 2. For a clearing of the line due to a fault inside the zone, zone number 1, there is no delay. We are transmitting immediately a command to the other relay to trip as well. So this is a direct command, and that's why we call it a direct under-reaching transfer trip. It's a direct command. You trip as well. And that will clear the fault from both sides, which is the proper way to clear a fault. Another type of clearing a fault is when a fault is being detected. It is at the very end of the line or even beyond the line. The command to trip is being replaced by a permission to trip. And that's why we call it a permissive overreaching transfer trip. So the command to trip is not immediate. It is a suggestion. Basically, it's asking, do you, relay number 1, is seeing the fault as I am, relay number 2? If it does, trip. But if you don't, maybe it's just a hiccup on the line and not a real fault. Another problem that we might see on transmission line is a power swing. A power swing is, for an example, when at 8 o'clock in the morning everybody is going to work and the entire industrial park is starting. Everybody is starting their machines. And we have an increase of current, but that increase is not a fault. It looks like a fault, but it isn't. So the relay is supposed to be sensitive enough and smart enough to identify it and not to trip. To do that, we measure the rate of change of the current in time. Because a fault is happening like this. But an overload is not. It's going gradually. So the relay is supposed to be smart enough to apply the calculation of di to dt, the rate of change of I, the current, as opposed to the rate of change of the current. And we will see the increase of current going sky high, going through the area where we have to trip, but it will not because it's happening slowly. And we will see that the current goes back. So the impedance is going down, 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 and then up again. If the relay is identifying this case, it will not trip. And this is a power swing. When it comes to current, that's what we might see. That's a power swing. The current is going up, but then it's repairing. It is repairing itself. If it is repairing itself, why to trip? If the relay will wait several more seconds, the hiccup will disappear. And that is exactly the duty of a distance relay. Measuring the impedance of the line and deciding based on that if we have to trip or not. And this is the summary of distance protection relays.